Here's an important topic I want to discuss. Alright. Keep this simple. On the y-axis, you have the total energy. Okay? Goes up, down. On the x-axis, what you'll have is time. Now I know time, as we understand it, past future, is non-existent. This is just a representative of objects in motion. Objects doing things, for instance. And with a star, you have its birth and you have its death. Or, as I like to call it, big, long metamorphosis work. Okay? In the beginning, when a star starts off as a bunch of material, it's diffuse. Okay? Something really strange happens to it. I don't know if a lot of electric current passes through this, magnetically confines the material, but this diffuse bunch of matter down here has a lot of energy in it. And some process allows it to clump together really violently. And what happens is the star is born. And the amount of time that the star is born in is relatively short. I'd say maybe about that long. There isn't any scale for this because it's purely conceptual at the moment. But as far as I can see, the total energy of the system increases very violently. So birth is violent. Very, very violent, very, very bright. We should be able to see stars that are born. Whether or not we call them supernova or nova, not too sure at the moment, but I'm pretty sure the stellar birthing process is very violent and hot. It takes a lot to birth a star. It just doesn't appear. And after it's born, it has a lot of energy. Okay, it's up here. And so now, since this is a very time-consuming process, what happens is the star cools and dies and radiates away. It loses its mass at a slow pace. Now, I didn't make this long enough, but you get the point. This is stellar evolution. So what you have is the total energy of the system going up significantly as it's born. It reaches a point of equilibrium where it can get as big as it can. So this is where all the blue giants are, all the really big stars. And this is the maximum diameter those stars can be. Max. Based off of however large this initial material, how much material was there. And over time, the big hollow shell, which expanded, so it started really small down here, say like a white dwarf, which expands, gets bigger and bigger and bigger really quickly, and then it reaches equilibrium, and it starts cooling, shrinking, and dying. Now, I remember I put an initial paper, calling out Jeans' mass and Jeans' instability as pseudoscience, because what they do is they have a gravitational field already present inside where this initial cloud of gas is. That's bullshit. There is no gravitational field here. To clump the material together, absent a gravitational field, you have to use electricity and magnetism. Those are the two things that birth a star, not gravitation, because there's no gravitational field here. Okay? Gravitational field takes over once the star is formed, and then the gravity keeps it together. And what happens is the gravitational field is really strong right here because it's holding all that stuff together. And then it expands, gravitational field diminishes, and then it keeps on diminishing as the star cools, shrinks, and dies. And I don't know if you remember this, but on the Hertzsprung-Russell diagram, I had it to where, the star starts up here and then cools and dies, and then the planets are the ones that you can't see because they don't have spectrums. Okay? So what I'm proposing is that the white dwarfs on those things start out over here. The star starts out right here with its luminosity. And then it goes up, fully expanded, this point right here, and then it comes back down again, and then eventually moving out of the visible spectrum. And I think one of the most important things about this is that the birthing process, where it gets an initial heat, is during its birth. The birthing process is where it receives the majority of its heat, which means as it evolves, guess what? It doesn't have a power source. It's a dissipative structure. It's not nuclear, and it's not powered externally. Not nuclear, but a star next to that, and it's not powered externally. And since it's not powered internally or externally, we can have whatever process births it as the initial energy. Okay? So what you would need to do is calculate how much energy would be in, say, a molecular cloud. Or you determine how much energy it would be required to, say, magnify the cloud or magnetize the cloud with electrical current. So you could put electrical current as the main driving process to pinch that cloud together, forming the white dwarf, which then expands to a blue giant and then starts cooling as it reaches equilibrium. That's basically it. Short birth, long death. Takes a very long time for the star to die.